Hello and welcome to Lecture 2 of Advanced Topics in Quantum Information Theory. This lecture is on the topic of quantum max relative entropy and conditional min-entropy. Before we discuss quantum max relative entropy, let's take a moment to think about the ordinary quantum relative entropy, which you will recall is defined as you see here. Now, there are intuitive ways to describe what this function means or represents. It's kind of like a loss of efficiency when you plan for Q, but you get P instead. But we really don't need to concern ourselves too much with any sort of concrete meaning of the quantum relative entropy. The fact of the matter is that it is an incredibly useful function through which we can understand various properties of von Neumann entropy, quantum mutual information, and so on. In particular, the formulas that you see here, combined with known properties of the quantum relative entropy, allow us to prove fundamentally important facts concerning the von Neumann entropy, the conditional quantum entropy, and quantum mutual information. In fact, you can, in some sense, think of the quantum relative entropy as being the more general notion from which these specific quantities arise. A highly noteworthy example, of course, is that through the joint convexity of quantum relative entropy, we may conclude that the von Neumann entropy is strongly subadditive, as well as closely related facts such as the data processing inequality. Of course, the proof that the quantum relative entropy is jointly convex is not so simple, but we did cover it in the Theory of Quantum Information course. We'll actually see an alternative proof of the joint convexity of quantum relative entropy coming up in a few lectures that makes use of the quantum max relative entropy, but first we need to cover some relevant material. Now, the quantum relative entropy and the entropic quantities that it defines, in particular the conditional quantum entropy and the quantum mutual information, have operational meanings or interpretations in the so-called IID limit. That is to say, these quantities generally tell us about what happens when an increasingly large number of independent copies of a given state is made available. That is, they tell us about asymptotic behavior. For example, in the setting of source coding, we imagine that we have n registers, x1 through xn, each being independently in the state row. You could say that the registers are independently and identically distributed according to row. We don't typically use the word distributed in the quantum domain, but this is what is meant by the term IID in this context. What we seek in the setting of quantum source coding is a way to compress the states of these n registers, which could be correlated with external registers that we can't influence, into m qubits, y1 through ym, in such a way that a high-fidelity decompression is possible. Of course, that means preserving whatever correlations exist with external registers, which makes this a non-trivial task. Schumacher's theorem, which is essentially the quantum extension of Shannon's source coding theorem, tells us that a high-fidelity compression scheme is either possible or impossible, depending on how the code rate compares with the entropy of rho, for all but finitely many values of n, or, equivalently, for sufficiently large values of n. The key here is that the entropy is telling us about the possibility to compress and decompress with high fidelity in the limit as n goes to infinity. The theorem statement doesn't say anything at all about small values of n, and in particular, it says nothing at all about the case n equals 1. This is one of the principal motives behind the max relative entropy, as well as some other variants of the relative entropy that we will discuss later. The max relative entropy is a function that shares many of the characteristics of the ordinary relative entropy, as we will see, but it is in fact relevant in the non-IID setting, or the so-called one-shot setting, where we are in fact concerned with the case n equals 1. Cryptography offers many good examples where a focus on the one-shot setting, as opposed to the IID setting, is justified. For instance, it's not good enough to choose a high-entropy password. Imagine you need to choose a new password, and you decide to choose the password ABC123 with probability 1/2, and otherwise you choose a long string of characters uniformly at random. It's a very high entropy distribution you're sampling from, but it's a terrible strategy for password generation. With probability 1/2, you'll end up with a lousy and insecure password. It's much better to choose a password having high min-entropy, which is a quantity that can be derived from the max relative entropy and that we will encounter later. Although the max relative entropy is applicable in a one-shot setting, the ordinary quantum relative entropy can in fact be recovered from the max relative entropy, or really a so-called smoothed variant of max relative entropy, by applying it in an IID setting and taking the limit as n goes to infinity. Now let us move on to the definition of the max relative entropy. We define this quantity for a density operator ρ and an arbitrary positive semi-definite operator q. We're not going to bother to try to define this quantity when the first argument is not a density operator. Given ρ and q, the quantum max relative entropy of ρ with respect to q is defined as the infimum over all real numbers lambda for which ρ is less than or equal to 2 to the lambda times q, where less than or equal refers to the positive semi-definite ordering. Now, it is possible that there are no real numbers lambda for which that inequality holds, for some choices of ρ and q, and that's okay. As usual, we define the infimum over an empty set of real numbers to be positive infinity. Indeed, it is not hard to see that the quantum max relative entropy of ρ with respect to q is finite if and only if the image of ρ is contained in the image of q. Of course, the image of ρ being contained in the image of q is equivalent to the kernel of q being contained in the kernel of ρ, and you will sometimes see this condition expressed in this way. But either way you express it, you will note that this is exactly the same condition under which the ordinary quantum relative entropy is finite. By the way, as you may have noticed, we tend to drop the word quantum when speaking of the quantum relative entropy or the quantum max relative entropy. Typically, we just refer to the relative entropy or the max relative entropy with the understanding that we mean the quantum analog of these functions when they take positive semi-definite operator arguments. Now, if we take a look at the definition, we see immediately that it is possible to express the max relative entropy in terms of a semi-definite program. Specifically, the max relative entropy of ρ with respect to q is the logarithm of the optimal value of this semi-definite program. The primal problem clearly represents the exponential of the max relative entropy as we just defined it, and I have just computed the dual problem offline and obtained what you see here. Of course, if you are so inclined, I encourage you to pause the video and compute the dual yourself and check that you obtain the same result. It is also possible to express the max relative entropy through a slightly different semi-definite program. The negative logarithm of the optimal value of this semi-definite program is equal to the max relative entropy. This is quite straightforward, in fact. You will notice that the two semi-definite programs are, in some sense, reciprocal to one another. Notice that all four of these problems are strictly feasible in the case that the image of ρ is contained in the image of q, and so strong duality follows from Slater's theorem for both semi-definite programs. If the image of ρ is not contained in the image of q, then we still have strong duality. We can just examine that the primal and dual optimal values agree in these cases, positive infinity in the first semi-definite program and 0 in the second. There are a couple of alternative ways to express the max relative entropy that we will now take a moment to note. For the first, we can observe that in the case that the image of ρ is contained in the image of q, the condition that ρ is less than or equal to 2 to the lambda times q with respect to the positive semi-definite ordering can be expressed in a different way. Specifically, this inequality is equivalent to the spectral norm of ρ conjugated by the square root of the Moore-Penrose pseudo-inverse of q, being at most 2 to the lambda. We could, of course, replace the norm with the largest eigenvalue, given that the operator that we're talking about here is positive semi-definite. But in any case, we obtain the expression that you see here for the max relative entropy of ρ with respect to q. For the second alternative characterization of the max relative entropy, we note that the same operator inequality that we had before is equivalent to saying that the inner product of ρ with z is at most 2 to the lambda times the inner product of q with z for every positive definite operator z. And from that observation, and assuming that q is non-zero so that we're not dividing by 0, we find that the max relative entropy of ρ with respect to q is equal to the supremum over all positive definite operators z of the logarithm of the ratio between the two inner products that we just mentioned. That isn't surprising if you think about either of the dual problems from the previous slide, but it is a handy expression to have. It is natural to ask at this point, what is the intuitive meaning of the max relative entropy? One way to think about it is as follows. Suppose that we have a density operator ρ and a positive semi-definite operator q, and we imagine different ways that it might be possible to express Q as a non-negative linear combination of rho and some other collection of positive semidefinite operators. And because we're focused on the relationship between rho and Q, let's just imagine that there's one other positive semidefinite operator called R, and that we have an expression for Q as you see in this equation. Q equals eta times rho plus R. The largest that we can possibly make eta in any such expression is precisely 2 to the negative max relative entropy of rho with respect to Q. Notice that if Q is also a density operator, which we might denote by sigma rather than Q to help us remember that it is a density operator, then eta can be at most 1. In this case, we can think about the quantity 2 to the negative max relative entropy of rho with respect to sigma as being the maximum probability that we could associate with rho in any convex combination of density operators including rho that yields sigma. Of course, that probability can be set to be equal to 1 if and only if rho and sigma are equal, and otherwise this probability is less than 1. And so we obtain an analog of Klein's inequality for the max relative entropy. At the other end of the spectrum, if rho and sigma are very different, or let us say highly dissimilar, then any convex combination of states that includes rho and yields sigma must associate a very small probability with rho. And that means that the max relative entropy of rho with respect to sigma has to be large. In this way, as you would expect from a function having a similar nature to the ordinary relative entropy, the max relative entropy represents a measure of dissimilarity, where a large value indicates a high degree of dissimilarity. Next, let us consider the monotonicity of max relative entropy under the action of channels. Before we do that, let me say that we cannot prove that the max relative entropy is jointly convex, because it isn't, and in that respect it is different from the ordinary quantum relative entropy. It is, however, jointly quasi-convex, meaning that the inequality written here is always satisfied. Monotonicity with respect to channels, on the other hand, always does hold. And by that we mean that the max relative entropy of phi of rho with respect to phi of Q is upper bounded by the max relative entropy of rho with respect to Q for every channel phi. In fact, complete positivity isn't required for this inequality. It holds for all positive and trace-preserving linear maps phi, not just for channels. This is almost immediate, in fact, from the definition. If rho is less than or equal to 2 to the lambda times q for some choice of lambda, then by the positivity of phi, it must be the case that phi of rho is less than or equal to 2 to the lambda times phi of q. And from this, the inequality follows. We didn't actually need phi to be trace-preserving for this argument, but because we have only defined the max relative entropy when the first argument is a density operator, we do need phi of rho to have trace 1 in order for the max relative entropy of phi of rho with respect to phi of q to be defined. Next, let us see how the max relative entropy compares with the ordinary relative entropy. There is, in fact, a very simple relationship between the two, which is that the max relative entropy is always at least as large as the ordinary relative entropy. There are different ways to prove this. One way is to use the operator monotonicity of the logarithm function, which means that if p and q are positive definite operators, for which p is less than or equal to q, then log of p must also be less than or equal to log of q. It's not trivial to prove that statement, but we won't go through a proof because it's a bit tangential to what we're talking about. It is a well-known fact, though, and you shouldn't have any trouble finding a proof in case you're interested. Once we know that the operator logarithm has this property, the fact that the relative entropy is upper bounded by the max relative entropy is pretty straightforward. Specifically, if we have a lambda such that rho is less than or equal to 2 to the lambda times q, then we simply write down the definition of the ordinary relative entropy, use the operator monotonicity of the logarithm to conclude the inequality that you see here, and the resulting expression evaluates the lambda. And because this is true for every lambda for which rho is less than or equal to 2 to the lambda times q, we obtain the required bound by minimizing over all such lambda. As I suggested, that's not the only way to prove this bound. There's another way to do it, for example, that uses the operator monotonicity of the square root function, which is perhaps a bit easier to prove than the operator monotonicity of the logarithm function. Finally, let us observe a couple of additional facts concerning the max relative entropy. First, the max relative entropy is additive with respect to tensor products in the sense that this formula that you see here is satisfied for all choices of row 0, row 1, q0, and q1. A simple way to prove this fact is to use one of the alternative characterizations of the max relative entropy that we saw earlier, in particular the one that is shown here. Observe in particular that the max relative entropy of row tensor n with respect to q tensor n is equal to n times the max relative entropy of row with respect to q. Of course, the ordinary relative entropy is also additive with respect to tensor products in precisely the same way. There is also a simple formula for the max relative entropy of two block diagonal operators, as is shown here. More generally, if we have any ensemble of states, and we consider the max relative entropy of the corresponding classical quantum state with respect to some operator q having a similar block diagonal form, the result is equal to the maximum value over all of the blocks of the max relative entropy within that block plus the logarithm of the corresponding probability. This is helpful both for evaluating the max relative entropy in such a case and for developing a bit of an intuition for how the function behaves. In contrast, here is the formula for the ordinary relative entropy for block diagonal operators of the same form. Note, by the way, that if the second argument also includes the coefficients p1 through pn within the blocks, then we obtain these somewhat simpler looking formulas, which happen to nicely reflect the essential character of these functions. Informally speaking, the max relative entropy, true to its name, is based on the max function, whereas the ordinary relative entropy is based on averages. And that's about all we'll say about the max relative entropy for the moment. If we were to briefly summarize our discussion of the max relative entropy in the form of a hypothetical cheat sheet for an exam that doesn't exist, we might include the following facts. First, we have the definition of the max relative entropy, along with a couple of alternative characterizations of it. In the first alternative characterization, I've written an inverse of Q rather than the more Penrose pseudo-inverse of Q as a somewhat informal way of suggesting that the function takes infinite values when the image of rho is not contained in the image of Q, as if the norm would take an infinite value in that case. We also have an analog of Klein's inequality when the second argument is a density operator. And we know that the max relative entropy is monotonic with respect to the action of any positive and trace-preserving map, meaning that applying any such map to both arguments cannot increase the value of this function. Also, the max relative entropy is lower bounded by the ordinary relative entropy. And we have these formulas for the max relative entropy of tensor products and block diagonal operators, as we just discussed. Finally, I've included the value of the max relative entropy for scalar arguments, which is handy when combined with the formula for block diagonal operators, as it yields a formula for the max relative entropy for diagonal operators. That is, you can consider the case where the rho sub k's are all 1 and the q sub k's are all scalars, to compute the max relative entropy for a diagonal operator. Of course, the formula we obtain is entirely consistent with the way that we define a classical version of the max relative entropy for vector arguments. Now we'll move on to the conditional min-entropy, which will be defined in terms of the max relative entropy. It will be helpful to begin with a fact about the ordinary conditional quantum entropy, or really it's a fact about the quantum relative entropy. Observe first the definition of the ordinary conditional quantum entropy in terms of the quantum relative entropy. And now the fact that we wish to observe is that the reduction of rho to y, which is tensored with the identity in the second argument, is in fact the density operator that achieves the minimum value of the quantum relative entropy ranging over all possible states of y. That fact remains true even when the identity operator on X is replaced by any fixed positive semidefinite operator, and that is a good exercise that I will leave to you. With that fact in mind, we define the conditional min-entropy in an analogous way, substituting the max relative entropy for the ordinary relative entropy. That is, the conditional min-entropy of x given y, assuming that the pair of registers xy is in the state rho, is what you get if you minimize the max relative entropy of rho with respect to the identity on x tensored with sigma on y over all density operators sigma, and then negate that quantity. Unlike the ordinary quantum relative entropy, the reduction of rho to y might not actually achieve the infimum in this case, but the infimum will always be achieved by some density operator sigma, and that fact will become clear in just a moment. Now, if we unwrap the definition of the max relative entropy and write everything explicitly, we have the following expression for the negative exponential of the conditional min-entropy. We can simplify this expression a bit by merging eta and sigma into a single variable y, being equal to eta times sigma. Of course, we then range over all positive semidefinite operators y and replace eta by the trace of y. That's quite obviously a semidefinite program, and we'll get back to that very shortly, but we might as well just take a brief moment to observe that the conditional min-entropy is upper bounded by the ordinary conditional quantum entropy, which follows immediately from the fact that the max relative entropy upper bounds the quantum relative entropy. Now, concerning the expression we just considered, it is, as we noted, the optimal value of a semidefinite program, and here is such a semidefinite program. For the sake of convenience, I've allowed our expression to be reflected directly by the dual problem, and part of the reason for doing that is that we obtain a very familiar-looking semidefinite program. It is, in fact, an instance of the optimal channel semidefinite program, which, of course, we also use for optimal measurements. This semidefinite program is strictly feasible in both the primal and the dual, so strong duality always holds, and the optimal values are achieved in both the primal and dual problems by Slater's theorem. And that, by the way, is how we know that the infimum in the definition of the conditional min-entropy is achieved. Notice that rho defines the primal objective function, whereas the constraints in the primal problem simply enforce that we're optimizing over all x that are Choi representations of channels, from y to x in this case. Now, that's already somewhat intuitive, but we can in fact think about this optimization in a slightly different way that gives a really useful and perhaps much more intuitive way of thinking about the conditional min-entropy. In order to explain this, it's going to be helpful to make use of the notion of the transpose of a channel, or the transpose of any linear map from square operators to square operators for that matter. So let's assume that phi is any linear map from linear operators acting on y to linear operators acting on x. We'll define the transpose of phi to be the uniquely determined linear map from L of x to L of y that satisfies the equation that you see here. Simply put, phi transpose is the map whose Choi representation is what you get by applying phi not to the left-hand side but to the right-hand side of the unnormalized maximally entangled state on two copies of y. Choi representations are, of course, unique, and that's why phi transpose is uniquely determined by this equation. Now, it is the case, as you might have hoped, that the transpose of phi is exactly what you would get if you took any Krauss representation of phi and transposed all of the Krauss operators. And that's pretty easy to see if you think just for a moment about how Krauss representations and Choi representations are related, along with an identity concerning the Vec function that gets used about 1,000 times in the Theory of Quantum Information course. And so the transpose of a map is, in fact, aptly named. Now let's make a short list of simple facts concerning the transpose of a map. First, the transpose of the transpose is, of course, the original map. The mapping you get from this transposition operation is itself a linear map, and it's one-to-one and onto. Next is the fact that transposition preserves complete positivity. And finally, the transpose of phi is unital if and only if phi preserves trace. Now that we're armed with that S-stock, we're ready to better understand the primal problem of our semi-definite program. Let's take a look, in particular, at the primal feasible set. It contains precisely the Choi representations of channels from y to x, and we can flip the channel to the opposite tensor factor by replacing it with its transpose. Of course, as we range over all transposes of channels from y to x, we're simply ranging over all completely positive and unital maps psi from x to y. Now, remember that the optimal value of the semi-definite program is the negative exponential of the conditional min-entropy of x given y, and so we have this expression for this quantity. We can now flip psi to the other side of the inner product by taking its adjoint, and we obtain this. Of course, as we range over all completely positive and unital maps psi from Lx to Ly, the adjoint psi star ranges over all channels from y to x. Here I've used the letter psi to refer to the channel. Now, if we follow the argument from the beginning, we don't get that the channel psi is equal to the channel phi. It's actually the adjoint of the transpose, which I presume that we would call the complex conjugate of phi. Anyway, by normalizing the second argument in the inner product, we see that the expression that we have obtained is equal to n times the sup, or the max, over all channels psi from y to x, of the squared fidelity of the state that results from transforming y into a second copy of x in accordance with psi, with the canonical maximally entangled state that I've here named tau. And that is the interpretation or the characterization that we were going for. You're given a single copy of rho, which is a state of a pair of registers xy, and you try your best to transform y into a second copy of x, so the state that you get, or let us say distill, has high fidelity with a copy of the maximally entangled state tau. The conditional min-entropy of x given y is the negative logarithm of the dimension of x times this maximum fidelity squared. Let's finish off the lecture by looking at some examples. First, let's imagine that y is trivial, meaning that its corresponding complex Euclidean space is one-dimensional. In that case, rho is just a density operator on x, and the conditional min-entropy of x given this trivial register y looks like this according to the definition. But there's actually only one state sigma of this trivial register y, and that is the scalar 1. So we can ignore this state altogether, and we obtain -1 times the max relative entropy of rho with respect to the identity operator on x. And if you think about that for a moment, you'll find that this is the negative logarithm of the largest eigenvalue of rho. Of course, we omit the register y from the notation in this case, and we just call this the min-entropy of x, or the min-entropy of rho. If you've ever encountered the min-entropy for probability distributions, this is exactly how you would expect this quantity to be defined for quantum states. Next, let's imagine that rho is a product state of x and y. Let's say sigma tensor psi, for those being states of x and y respectively. Well, it's actually a pretty similar calculation to the one that we just went through. We take the definition of the conditional min-entropy, and it's not hard to see that the infimum over all psi prime is achieved when psi prime equals psi, and we obtain the same expression as before, the min-entropy of x. This is very natural, of course, because if x and y are completely uncorrelated, then we don't expect the state of y to have any influence or relation on the state of x, and so the conditional min-entropy is just the min-entropy of x. Next, let us suppose that we have a separable state rho, so there's no entanglement between x and y, but there could be classical correlations. Then, of course, if we were to apply the channel psi to y, we'll be left with another separable state, because the action of psi is local. This implies that irrespective of psi, the fidelity squared between psi applied to the y part of rho and the maximally entangled state tau must be bounded. It's at most 1 over n. If you took the theory of quantum information course, then you will recall that we did prove that fact right before we discussed measures of entanglement. In fact, we proved a more general statement, which is that if we take any state and we look at its squared fidelity with the maximally entangled state, then the quantity we get is always upper bounded by the entanglement rank of that state divided by n. In the case at hand, this means that the conditional min-entropy must be non-negative. Now, don't hold out any hope that the conditional min-entropy might offer a characterization of entanglement, because we can repeat exactly the same calculation for PPT states in place of separable states, and we achieve the same bound. And of course, PPT states include non-separable states in general, unless x and y both have very small dimension, specifically their sum being at most 5. Next, as perhaps an obvious example, we can consider the situation where tau can be recovered exactly from ρ by applying some channel psi as before. That statement happens to be equivalent to ρ having the format you see here. In short, ρ has to look like we took tau, tensored some garbage state psi to it, and then embedded half of tau along with psi isometrically into y. By our alternative characterization of the conditional min-entropy, we find that in this case, the conditional min-entropy will be negative log n, for n being the dimension of x. And that is, of course, the minimum possible value that the conditional min-entropy can take. By the way, the ordinary conditional quantum entropy takes exactly the same value for any state ρ of this form. Perhaps I should also mention that the maximum possible value of the conditional min-entropy of x given y over all choices of ρ is positive log n, and that statement is also true for the ordinary conditional quantum entropy. Finally, let's consider the situation in which ρ is a classical quantum state, with x being classical and y being quantum. Once again, using our alternative characterization, and this time simplifying using the fact that ρ is classical quantum, we obtain this expression. Nothing changes, by the way, if we restrict the supremum to quantum to classical channels psi, or in other words, channels psi that represent measurements. And so we see that the value is precisely the optimal correctness probability to discriminate a state chosen randomly from the ensemble corresponding to ρ. The min-entropy is then the negative logarithm of this optimal guessing probability. If you can discriminate the states with high probability, then the conditional min-entropy will of course be non-negative, but small, 0 in the case of a perfect discrimination. And that is what you would expect from a quantity measuring your uncertainty about x given y. And it will be large when the optimal guessing probability is small. That's it for this lecture. As always, be sure to let me know if you have any questions, and thanks for watching.